Welcome back. At the end of the last class, we discussed the moment of inertia. The moment of inertia is the analog of mass for a rotational motion. If something has a very large moment of inertia, then it will take a large amount of force perpendicular to the rotational axis to cause it to accelerate. It also means that an object with a large moment of inertia is turning, then it will be difficult to stop its rotation. So it has lots of inertia. Something has a large moment of inertia when the object has a large amount of mass that is far from the axis of rotation. In the last class, we talked about how to find the moment of inertia of a bunch of point masses, and here we want to look at the moment of inertia of a few common shapes. The moment of inertia of a single mass at a point is the mass times the radius squared. So symmetric objects, where the rotational axis goes through the center of the object, tend to have moments of inertia that are proportional to the mass times the radius squared. For this reason, we often use a parameter called beta, so the Greek letter for b, and this beta is determined by the shape of an object, and to get the moment of inertia, we can multiply this beta value by the mass times the radius squared of the object. Our first shape of interest here is a ring. So in a ring, all of the mass of the object is at a distance r from the center of the ring. So remember, the moment of inertia that we are finding here is the moment of inertia for the ring where it rotates around the center of the ring. Imagine a bicycle wheel here where nearly all of the mass is in the tire and the wheel, and very little of the mass is in the spokes. Anyhow, the moment of inertia of a ring is mr squared. This should sort of make sense. All of the mass is at a radius r from the center, so the moment of inertia is the same as for a single particle with the mass m and a radius r. The beta parameter here is 1 because the moment of inertia is 1 times mr squared. Our next shape is a disk or a cylinder. So the moment of inertia for a cylinder or a disk is 1/2 mr squared. So the beta parameter for a disk is 1/2. The reason that the moment of inertia is smaller for a disk than a ring with the same mass and radius is that the mass in the disk is spread out over the entire disk. So much of the mass is much closer to the rotational axis than the edge. For a ring, all of the mass is at a radius of r from the rotational axis. Again, the rotational axis is through the center of the disk, so it is rotating like a wheel. If we picked some different rotational axis, then we would have a different value for beta. Our next shape here is a sphere. So we're going to consider two cases for a sphere, one where the sphere is solid and one where the sphere is hollow. The solid sphere has a moment of inertia of 2/5 mr squared, and the hollow sphere has a moment of inertia of 2/3 mr squared. So the beta for the solid sphere is 2/5, and the beta for the hollow sphere is 2/3. It should make sense that the hollow sphere has a larger beta than the filled sphere. In the hollow sphere, the mass is further away from the rotational axis than the solid sphere. Notice that the rotational axis goes through the center of the balls, so the betas for the sphere are smaller than that of a ring, because even in a hollow sphere, parts of the ball have a much smaller distance from the rotational axis than the radius. For an example of this, think about the Earth. So at the equator, the distance from the rotational axis is the radius of the Earth, so something like 6,400 kilometers. But at the North and South Pole, you can actually stand on the rotational axis, so your distance from the rotational axis will then be 0. So the moment of inertia depends on this distance to the rotational axis. All right, so I think I want to walk through a moment of inertia example here. So here, the moment of inertia for a solid sphere with a mass of 5m and an axis of rotation through the center of the sphere with a radius is 2r. So the question is, what the moment of inertia is how many mr squared? Okay, so first we're going to need the formula for the moment of inertia of a solid sphere. That is the moment of inertia I is equal to 2/5 times mr squared. The thing that tends to trip people up in questions like this is that the radius here is 2r, so the square of the radius is 4r squared. The r variable contains a number, so you need to square it as well. You need to square the 2 as well. So that means if we want to solve this, we find that our moment of inertia is 2/5 times mr squared, so that becomes 2/5 times 5 times the mass times 2r squared, which becomes 4r squared. So that means that this becomes 2/5 times 5m times 4r squared. So the moment of inertia here is 8mr squared. Okay, so now it's your turn. You have at least 2 of these to do with rings and disks, so good luck.